Hi, today we are going to talk about the limits, and this is an important notion because we will define derivatives and integrals using the idea of limits. So, what is the limit of a function? Here is a definition. So, let's say we have a function f of x, which is defined around the number a. Well, this a may not be an input, but all the numbers around a are inputs. So A may or may not be, but all the numbers around A must be inputs. So then we write limit of the function f of x as x approaches to A is equal to L. And then we say the limit of f of x is L as x approaches to A. But this is mathematically when the input values x approach to A, so the input values x are approaching to A, we are not talking about A, we are talking about the input values x approaching to A, then the output values of f of x of these input values get closer to L. This is the limit of a function at A. Okay, so here is a pictorial description. Like, let's say we have a function f of x. So this circle here means f is not defined at a. Okay, so f is not defined at a. Well, it can be also defined, but the limit doesn't care about whether the function is defined or not. It cares about what happens to the output values of the numbers around a. So when we look at these yellow, I labeled them with yellow and green ones. So the yellow ones are output inputs which are smaller than a. So x1 is small, x2 is smaller than a, but x2 is bigger than x1, but still smaller than a, and x3 is smaller than a, but bigger than x2. So x1 is close, but x2 is closer, and x3 is much more closer. Okay, and similarly, like x6 close to a, but x5 is closer, x4 is even more closer. So we are kind of approaching to a. So these are the inputs, these x1, x2, x3, x4, x5, x6. And then what happens to the outputs? So the images, the outputs, as you see, f of x1, f of x2, f of x3, they approach to this number L. Or look at f of x6, x5, x4. As you see, the outputs are approaching to L. So then we say the limit of f as x approaches to A is L. Okay, so that's what happens. We don't even need to have f to be defined at A, but we care about what happens to the output values of the numbers around A. When the inputs get closer and closer to A, the outputs of these inputs are getting closer and closer to this number L. If this happens from left and right of A, if these numbers, these outputs are the same output value, then we say the limit exists. Okay, so this is the definition of limit. Now let me give you like another example. For instance, let's say we have some function, but I will just draw a graph like this. So empty circle means the definition of the function is not equal to that number. So let's say this is 3, let's say this is 2. So f of 3 is equal to 2. But then, I mean, f of 3 is not equal to 2. That means, and, but f of 3 is in fact equal to, now I show it with field circle. Let's say it's equal to minus 4. Okay, and it goes this way. So f of 3 is equal to minus 4, not 2. So the empty circle means f is not defined as 2 at 3, but it's defined as -4 with the full circle. And then it goes, let's say, somewhere like this. This is, let's say, happening at, let's say, 5. And then this value here is corresponding to -1, let's say, but still keeps going. Let's say this is a full circle and keeps going like this. And okay, let's give numbers here. Let's say this is 12, and let's say this value is 6. Okay, so when you have a function, a graph like this, if you look at the graph, and if you want to talk about the limit of, this is, by the way, the function f of x, if you look at x goes to 3, or as x approaches to 3, the function, well, from the left, like for the inputs which are smaller than 3, the outputs are approaching to 2. Like you see, they are approaching to 2. But from the left, I mean from the right, what do you see? The outputs are approaching to -4. So these two numbers are different. So the limit doesn't exist, we say. Or we also show it like this, like we write a minus on top of 3, which means the limit from the left, or the values of the outputs of the inputs from the left are equal to 2, but the output values of the inputs from the right of 3, which are with the green one, they are equal to -4. And these two output values are not the same number, so we say the limit as x goes to 3 does not exist. These two numbers from the left and from the right must be the same number. Okay, as you see from the left, so this minus is related to the inputs from the left of 3, so smaller inputs from 3, and then the green ones, they are bigger inputs than 3, or the right of 3, and as you see, the outputs from the right of 3 are approaching to -4. So they are not the same number. Then in that case, we say the limit of the function f as x approaches to 3 does not exist. But then look at 5. What happens from both left and right? The inputs, when we approach to 5 from left and right, the outputs will approach to -1, right? So let's draw that with some different color. So if we approach to 5, so the outputs are approaching to -1. Or if we approach to 5 from the right, let's do it this color here, then the outputs are approaching to, again, to -1. The same number here, right? So then the limit of f as x approaches to 5 is equal to -1, we say. So the limit, the limit of f as x approaches to 5 from the left and right is -1, So then we say the limit exists and it's equal to minus 1. So this minus 1, from the left I showed it with light blue, and so this minus f superscript minus means the inputs from the left of 5, or the inputs which are a little bit less than 5. And then I labeled with purple the numbers from the right of 5. So the numbers from the right of 5 are gonna be, of course, a little bit bigger than 5. So the meaning of this minus and plus means this, okay? So minus means numbers little bit less than 5, minus means. And the upper script plus means numbers little bit bigger than 5. If these two outputs are the same numbers, as you see, they are both minus 1. So then we say the limit is equal to that number, minus 1. And of course, we also say the limit exists. The limit at x, well, not that I should say, the limit exists. I should rather say shortly. But do you see, the function isn't defined at 5. Okay, let's look at the graph again. At x5, the function isn't defined. Or let me change this to like, okay. Okay, so I'm just gonna change the coloring of this thing here to something different. Like, I'm gonna make this empty circle. So that means, let's say the function isn't defined as 6 at 12, but let's say it's defined as something else. Let's say some other number, let's say minus 7. So the function may be defined, but it may be some different number. So definition of the function is one thing. So the function is defined as 7, minus 7 at 12, but the limit is something else. So I want to show it with that way. So the limit of the function as x approaches to 12, as you can see from both left and right, is equal to 6. And it exists. The limit exists. But remember, f of 12 is equal to minus 7. So as you see, the definition has nothing to do. So how the function defined at 12 or at the number isn't important. So how f is defined at 12, we don't care. We just care about what happens to the outputs around 12. Okay, so that's the difference of limit from the definition. So look at this graph back again. When the values are approaching to 12, what is happening? The outputs will be approaching to 6, right? As you see, they are approaching to 6. And however, the value is different. F of 12 is equal to minus 7. So we don't care about minus 7 there. We just care about what happens to the outputs of the inputs around 12 as they get closer to 12. So as you see, it's equal to 6. Okay. So the limit is 6, but the definition is minus 7. So as you see, the definition and the limit are two different things. Let's give some other number here, like let's say uh, let's say 8, and so what happens? Well, okay, so this is 8. Let's say the definition and the values approach to the same number. And let's say that number is 1. Okay, so then in that case, like the values around 8, the output values of the inputs around 8 approach to 1. The definition of the function at 8 is also 1. Okay, then the limit exists. The definition is also 8. That's okay, some other thing, but we say that the limit as x goes to 8 of the function is equal to 1. Well, f of 8 is also 1. We will call this thing later continuity if the definition. So look at this, these two are different, and it doesn't matter for the limit. For the limit to exist, we must have the same output values for the inputs of the left of the number and the right of the number to be the same number, but it's not necessary to have the definition equal to that number. But in this case, they are equal. So we say the limit exists. Actually, once we write the limit of f of a function as x goes to some number is equal to some number, that already means the limit exists. Okay. Well, in this case, they are also equal, but that's beside the point. That's going to be important when the continuity thing comes. So when these two are equal, when the definition and the limit are equal, we are going to call this thing continuity. So when the limit of f and the output value of f at a point are same numbers, are same values, then f is called continuous at that point. F is called continuous at that point. So we will come back to this thing, like what I'm saying is if x goes to a, this is the limit, and if the value of the function at a are same, then f is called continuous. So if the limit is equal to the definition of the function, as you see, the limit is also f of a. The function is also defined as f of a, whatever that number is. Then in that case, f is called continuous. And look back at our graph, like the limit exists at 8 and 12. At 12, the limit is 6. At 8, the limit is 1. At minus 5, at 5, the limit also exists. It is equal to minus 1. But at 3, the limit doesn't exist. Why? Because from the left, the outputs are approaching to 2. From the right, the outputs are approaching to minus 4. So the limit doesn't exist. But in terms of continuity, as you see, like at 3, the function isn't continuous. Continuous means you can draw the graph without having to hold your hand back when you are sketching the graph. So like, let's say we are sketching the graph, and then we have to hold back our hand, then jump back to minus 4, and then continue drawing again. But at 5, what happens? There is a hole there. So I have to hold my hand back, jump that hole, and then continue again. So there is no continuity there. At 8, okay, the definition and the limit are same. So I don't have to hold my hand back. So it's continuous. But what happens at 12? Okay, when I come to 12, I have to hold my hand back and jump to -7 and then jump back to 6 and draw the graph again. So as you see, it's not continuous except for 8. I mean, 3, 5, 12, not continuous, but 5, 8, 12 limit exists. 3 limit doesn't exist. So this is a very pictorial, very visual explanation, which would be helpful to understand the limit. Another example I can talk about is, sometimes you may have tables, let's say, uh, let's say, uh, f of x equals sine x over x. Let's say this is the function, okay? Sine of x. So if you make a table of values, x, sine of x over x, so guess the value. Okay, I should have written limit here. So the limit of x goes to 0 of the function sine of x over x. Okay, so if you make a table of values here from the left and right of 0, let's say minus 0.1 and then minus 0.01 and then minus 0.001, even closer. Well, as you see, this is undefined, so sine of x over x is undefined at 0. Why? Because think about it, you are going to have sine of 0 over 0. Well, dividing by 0 is undefined, right? So this is undefined. But then you can also approach from the right, like plus 0.1, plus 0.01, even closer, plus 0.001. And then when you look at the values here, you are going to see values like this. Okay, so what's happening here? Like it's undefined at 0, but when you are approaching to 0, the values are approaching, rounding, almost rounding to 1. Like, the calculators can round this number 0.999 to 1. And actually, when you use a calculator to sketch the graph of this function, you are going to see something like this. X, Y, as very obviously, it's undefined at 0, but the graph will look like this. Okay, so the values are gonna approach to 1, okay, but it's undefined at 1, so there is no definition at 0. Okay, so even though the values are approaching to 1, output values are approaching to 1, there is no definition at 0. Okay, and we just then see that the outputs are approaching to 1, so the limit of this function as x approaches to 0 is equal to 1. Okay, so we can make a guess like this, because we can also see from the table the values are almost rounding to 1. Okay, and if you look at the graph of the function, you will see a graph like this. There will be a hole on the graph when x is 0, but y values will be approaching to 1, so then we say the limit is 1. But as you see, there is no definition at 0. I mean, the function is going to get undefined, so it's not defined there. But the limit still exists. It's equal to 1. Okay. Um, okay, I will give more examples in the next video.